Hello, welcome everybody. Welcome to the fourth lecture of this series on AI and data science for COVID-19. My name is Sanjay Chawla, and I'm a research director in QCRI. And let me give you the agenda for today. What I'll do is I'll give you, like last time, go through this, the lectures that are coming subsequently, and then I'll introduce today's speakers, Stefano, Rizzo, Mohamad, Saad, and in the end, I'll also be giving a short presentation. So just to make sure with the house rules, so as an attendee, when you join the WebEx, your microphones are muted and they can only be unmuted by the host. But we really strongly encourage you to ask questions by typing them in the Q&A window on your right-hand side. Periodically, the session host, in this case myself, will ask the speaker to pause and answer questions. So if you put a question in the Q&A window, I know sometimes I'll stop them and ask them right away. Other times I'll wait till the end. Okay. And in the end, we'll all take questions, more questions from you. We really want to make this interactive. So we really hope that you'll ask as many questions as you like. So here is the schedule for the upcoming lectures. So next, on May 11th, there will be a lecture on the use of artificial intelligence for drug discovery, how people are using AI for drug discovery. On May 14th, there will be the impact, social media analysis, social media information around COVID-19. People are calling it the infodemic. So there'll be a very nice lecture about that. And then on May 18th, we'll have a panel, and the panel will talk about responding to global crisis in the age of data and information. So let me introduce you. So the first lecturers today. Actually, the order is Mohamad Saad will go first. He's a research scientist at QCRI with expertise in statistical genetics, biostatistics, and bioinformatics. He's actually taught a course in epidemiological modeling, and he has a lot of experience in this area. Followed by Stefano Rizzo, who's a postdoctoral associate at QCRI and works on deep learning and machine learning, and has worked in different, in many various projects. And then in the end, I'll add 15-20 minutes to about how to take these models and extend them to spatial data. So without further ado, I'll hand it over to Mohamad Saad.
Thank you, Sanjay, for the introduction. And let me share my screen. Just waiting to have the hand on this to share the content. Okay, here we go. Just to make sure, do you guys, do you see the screen?
Yes, we do. Thank you.
Okay, good. Thank you for the introduction. Today, we will be going to talk about epidemiological modeling for COVID-19. And it's not really specific to that. It could be applied on any infectious disease like influenza or chickenpox or measles and so on. The outline of the presentation I will start by presenting the SIR models, the SEIR model, and some extension of these models that I will explain later on. Stefano will take the hand and talk about fitting the models to the data and how to infer parameters using machine learning. And then Sanjay will finish by spatial extensions and a few take-home messages. So the forecasting models, these are typical models that are used to predict the outcome of an infectious disease or the spread and to be able to know the future of what will happen, right? And this is very important. And of course, you guys, I mean, when you look at the news, especially for COVID-19, you could see a lot of these curves, a lot of these observed data, and the question, what will happen in the future? How do we flatten this curve, right? And the curve that represents the number of daily cases or the number of current cases, which are different, and we will talk about this later. And a lot of different methods are being used for this, and the accuracy of this depends on the model, on the type of parameters you put in, and the type of countries, data, and so on. The two key methods in these forecasting models, the first one is curve fitting and extrapolation models. The second ones, which is the scope of this presentation, these are the epidemiological models, SIR and the SEIR. To the right here, there are a couple of examples. For example, the Imperial College, the non-pharmaceutical intervention model, it's based on an SEIR model. And the other example is the Institute for Health Metrics and Evaluation. They use a curve fitting and extrapolation. So before I go into the SIR model, I will give a brief overview of the curve fitting and extrapolation. So the way how this works, you look at the data for today and the past, right? And you try to infer some trends about the epidemic by looking at the current status. You apply some mathematical approximation for the future using some experience from other locations, assumption about the population, transmission, and public health policies. All what you should bear in mind in here, when you apply some assumptions or some experience from other countries that are very different from your own country, this model will not work very well. If you don't account for the population size, the transmission rate, and different public health policies, the model will really give erroneous results. The second modeling, which we will spend time on explaining, are these epidemiological modeling. They aim to divide, they start by dividing the estimated population into different compartments or different groups. For example, the susceptible group and the exposed, the infected people, and then the removed or the recovered. These are the people who are not infectious anymore. And it applies a set of mathematical rules about how people move from one compartment to another using assumption about disease process, social mixing, public health policies, and other aspects. The first parameters I want to show before I go to these models, these are very important parameters that people should be aware of, and if they understand them, if they really know what they mean, it will make it easier for the remaining of the presentation. And it also helps on when you read some newspaper articles, they always talk about the basic reproduction number, which is R0, or some people pronounce it as R0. So this is the expected number of secondary cases produced by a single infection in a completely susceptible population. This means if you have one infected person, how many infection will result from this, right? So if this number is high, it's not as good, right? Because it means the infection will be spread very fast. The second rate, the second number I want to show is the transmission rate. We call it beta. And don't worry about these parameters. You know, if you are not familiar with math or something, these are easy. I will walk you through. The beta is equal to tau times C bar. And it makes sense by saying that tau is the probability of infection given a contact with an infected person. So you meet someone who is infected. What is the probability that yourself will get infected? That is tau. And the C bar is the average number of contacts per day between infected and susceptible people, right? So if you meet 10 people who are infected, and of course, the probability of transmission or the rate of transmission will be higher, right? The third rate is the removal rate. So we have the transmission, the people who get infected, the removal, there are the people who get removed, right? They are not infectious anymore, or they are recovered. This is gamma, and it's equal to 1 over D, and D is the duration of infectiousness. Okay, so when we know these three parameters, it's easy to see, or the R0 is defined by beta over gamma. So this is kind of a ratio between the two rates, transmission rate on the top and removal rate on the bottom. And you can imagine if beta is greater, right, which means the people who are infected is bigger than the people who gets removed, right? So the newly infected people are bigger, which means we will have a spread or we will have an epidemic that I will mention in the next slide. So this ratio, if it's greater than 1, we can see what will happen. But in any case, the aim is to decrease this R0. When we don't have many secondary infections, it is good in order to contain the progression of the infection. So look at this formula again and look at the three parameters. The parameter D, the duration of infectiousness, can be lowered if an efficient drug is available. There is no evidence for COVID-19 yet. And an example, it could happen for other influenza. You could be infected, you know, you have the virus, and the infectiousness period is when you can infect other people, right? For some types of influenza, you have the Tamiflu drug, and the duration will move from 5 days to 3 days, for example. You only infect for 3 days. For COVID-19, we are not sure yet if there is a drug that can lower this duration. And even though we have been hearing about remdesivir or the other kind of drugs that are being treated, prescribed for patients. The second parameter, which is tau, the probability of getting infected can definitely be lowered by wearing a mask, by washing hands regularly, etc. So mainly when you meet with someone who is infected, you know, if you wash your hands, if you keep your distance, if you wear a mask, this probability will get smaller. And the final one is the C-bar. The average contact number can also be lowered by social distancing. So if you stay home, you don't meet with people and likely will not meet with infected people. So if we can lower any of these, R0 will be lowered, and then we will be able to contain the disease and minimize its impact. So the first compartmental model that I will be talking about is the SIR. That's the simplest one. It splits the population into 3 compartments, as you can see in this diagram. The first group are the people who are susceptible, that can be infected eventually, and they move from susceptible to infected compartment with a beta rate, right? Beta is the transmission rate. And then people from the infected compartment, they go to the second one, which is the removed, with a gamma transmission rate. I kept these on the top right, these rates, so you can follow them up or you can always remember them. So we model this with an ordinary differential equations that you can see on the left. You don't have to be very familiar with this to understand. Just I want you to look at the right equations to see what is happening. So the way we model it, it's very clear that today's number of susceptible people, you know, the ST plus 1, it's equal to yesterday's susceptible people minus the people who got infected. So we had susceptible people, and the people who got infected will get removed from this compartment, so they will go to the infected compartment. The number of infected of today is equal to the number of infected of yesterday, plus the people who got infected yesterday, minus the people who got removed from the infection. So there is, you know, if you leave from one compartment, you have to go to the second compartment, right? You cannot go anywhere else. The third one, which is the removal or the removed compartment, the people who are not. So actually, just let me put some comment about this. What I mean by removed are not really recovered. Recovery rate for COVID-19 is being 15 or 14 days. It could be more. Removed is mainly when you are not infecting people anymore, which is around 4 days or 5 days. You infect people for 4 or 5 days. So the removed people of today is equal to the removed of yesterday, plus the people, the infected people who got removed with a gamma coefficient. So this is simply the 3 equations that we use to model, and it's simple to model it actually. The way how we can see the R0, going back to the R0, if you know the derivative is the rate of change, right, of any curve. If it's positive, this DI, it means the infection is increasing. And if you do some math, you don't worry about this. It will just show you to the extreme right in here, R0 is greater than 1. That means there is an increasing number of infected individuals. And we will say an epidemic occurs if R0 is equal to 1. And then if epidemic occurs in many countries across the world, we will call it a pandemic, which was kind of declared by the WHO organization sometimes in February. The second thing to make sense of this R0, and honestly, you see this number a lot in the newspaper. So what happens, right? Like, is R0 equal to 2? Is it big enough, 3 or 4 or something like this? What happens on the peak? If you hear about the peak of the infection, that's when the highest number of cases happens, right? You can see here on this graph, that's where we have the peak. It's the biggest number of current infections. So actually, this number in here, when we are at peak, the fraction of susceptible people is equal to 1 over R0. Just give a small example. If R0 is equal to 4, at the peak, we will have 25% of susceptible people, which means 75% got already infected. So that shows you how many got infected. 75%, that's really a lot. And then if you have an R0 of 2, 50% of people will get infected at the peak. And of course, if it goes less, infection will be smaller. So the impact of R0 on the infection progression, I'm showing this in 3 graphs. It's a hypothetical population of 100,000 people. The initial infection, let's say we start with 100 cases, 100 infected persons. And then let me walk you through the different colors of what we are seeing here. It's easy probably to look at the middle one. When we have, so the black dots, the black curve is the susceptible people. These are who are not infected yet, but they could. The green curve, these are the people who got removed, which means they got infected and they finished infecting people. And the 2 main curves are the red one, which is the current infections, and the blue is the new cases. These are kind of different because the current infection could be, let's say, 10,000, but daily you have 1,000 or 500, right? So kind of the current infection is accumulation of what is happening. So the first thing, when R0 is equal to 1, we call it a stable state of the disease progression, which is really good. So the disease will not progress, right? You have 1 person who is infected, 1 person who is removed, and it keeps doing like this, so it will not progress. So when R0 is equal to 2, look what happens. The peak will happen at day 40, or let's say day 38 or something like this. So it takes 39 days to reach the peak. And at that point, we will have around 20,000 people who are infected. Remember, 20,000 out of 100,000. So around 20% of the population. And it took 38 days. Now look how devastating could be if R0 is equal to 4, which was the case, by the way. In Wuhan, I guess at the beginning, it was around 4 or 3.8. So it was very high. In this scenario, to the extreme right, it needs 19 days, right? Only 19 days, which means it's very fast, to reach the peak, which results in more than 40,000 current infection, which is a lot. Like at some points, you have half of the population who are infected with this. And of course, health system cannot handle this, right? So we can see now how it impacts, right? The change in R0. And our aim, I said, it will be decreasing R0, right? And it could be by social intervention, by social distancing, or wearing a mask, washing hands regularly, and so on.
Saad, I had a question. So you mentioned in Wuhan, initially the R0 was like somewhere close to 3.
Yes.
Right? So what's the typical R0, say, for influenza and you know?
Yeah, so that's a good question. Influenza is much lower than COVID-19. That's why, influenza, a lot of people die from it, right? The only difference with COVID is spreading very fast, which means R0 is being bigger for COVID-19. Other diseases, by the way, the chickenpox or the measles, these are having a bigger R0 than 4, actually. This could be really spreading a lot. Okay, so for R0 equal 4, the extreme left, there is no intervention, right? You saw what happens. In 19 days, you have 40,000 cases. If you make a mild intervention, now the mild intervention for me, I just assumed you divide R0 by 2, right? So which means, you could probably lock down some schools, or you stop schools, you close restaurants, but you keep airport open and stuff like this. And the severe intervention, I assume that it is R0 divided by 4. That's just to show how the infection will progress in this case. And the intervention happened at day 10. These are all assumptions I made, because in general, that's what will happen. Like after 5 days, people will say, okay, let's lock down, or 10 days and something like this. So the middle one, we can see after 10 days, right? We had around 15,000 infection or 10,000, and the disease will not progress much more. It will keep progressing a little bit, but it's slowed it down. The peak will happen at 22 days, right? And we still have around less than 20,000 infection. So it helped, but not much, actually. That's why we needed severe intervention. And you can see when we make real severe intervention, when we lock down probably everything for 10 days or something like this, we can see that the progression of the infection stopped. And the peak was already reached at day 10, with the biggest number of infection to be around 9,000, right? So this is, severe intervention at day 10, we reach the 10,000 limit. If you don't do any intervention, you will get to 40,000. You can see the scale, right? From 10,000 to 40,000, that's a lot. And if you intervene earlier on, it will be even better. So that's an example of when R0 is equal to 4. So I'm just showing another example. When R0 is equal to, so it means the progression of the disease is slower than the R0 equal 4, but still, if we look at the scale, this will be the worst when you don't have any intervention, and the peak will happen at day 40, right? Which is around, again, a little bit around 20,000 cases. For if you make a mild intervention, you will reduce it to, let's say, less than 1,000. And then if you make a severe intervention, you will kind of stop the progression in a couple of weeks. You will only reach 500 cases at that point, right? That's in this case. And the final example I will mention is when you have a stable, we call it a stable state of R0 equal to 1. We can see if there is no intervention, I said the disease will not progress much, right? So you have both of the infected and the removed people are getting in. So nothing mainly will happen. And if you make some mild intervention, it will decrease, of course. And if you make a severe intervention, it will also decrease. Okay, but R0, when it's equal to 1, it's not of a big problem for the health system. So these graphs mainly is when R0 is equal to 0.5. When you have an R0 that is lower than 1, the disease will go to extinct, right? So the disease will not be in there. And you can see in here, just let's look at the extreme right graph. In just 10 days, you had 100 cases, right, at the beginning. In 10 days, you had 40, and then just 20 days, you have nothing, right? But in any case, if R0 at the beginning was 0.5, you wouldn't be hearing about COVID-19. But actually, in Wuhan, when they applied a severe lockdown, it went from 3.5, it went to less than 1, and that's how they controlled the progression of COVID-19. Okay.
Saad, there was a question about what is the value of R0 in Qatar? You want to comment about that, or?
So this is, I'm not sure how much it will be, but is it around 2.5
I guess, initially, I guess the beginning of the epidemic, probably R0 is the same more or less is it the same for all the countries, or it can vary, or
Yeah, in general, it could be like a lot of, even in Italy at the beginning, they started to be at 3.5 or something like this. And just keep in mind that this value, it's an estimate, and a lot, like every kind of 2 days, you will see a new estimate, right? But I would say in Qatar, it was around 2. Other people who really work closely with these data will be able to give a better estimate on this. But it was mainly above 2.
Right. Thank you.
So the model I showed, it didn't have vital dynamics, which means we are not assuming that people are born or people die, right? So there are models that gets more sophisticated, or they represent more a real scenario. And what happens is simply, you just add the people who were born, right? And I added to the right now, the lambda is the birth rate and the mu is the natural death rate. When you are born, you get to the susceptible compartment right away, right? And in the susceptible, you might die from other causes, right? Car accident or any other disease. And death, natural death, will happen in any of these compartments, right? So this will be represented in these equations to the right. They are very similar to the one I showed, except with these red terms. So again, don't worry about these equations. If you look it up, the susceptible of today is equal to the susceptible of yesterday, plus the people who were born, right? Anyone who was born who will get to the susceptible, minus the people who were susceptible but who died from other causes, right? So this is the term that is added to model this. In the infection, the good thing is you will add this term minus mu I. So you have COVID-19, but you die from a car accident as well, right? It could happen. So you will remove these from the infected people, and the recovery, or the removed people, some people will be removed because of natural death. Okay, so from now on, probably I will not have more equations, which is probably good. So this is the SIR model.
Sorry, Saad, just on the previous slide,
Yes.
of course, if you're dealing with a short-term epidemic like COVID, at least in the, it's there for a few months, people typically don't model lambda and mu, right?
I agree. Yes, and it will not affect a lot, actually, to be honest. That's the thing. That's why in any of these models, they don't account for this. But just I wanted to show that how these models could integrate more parameters or more realistic scenarios. But you are totally right. There are
a few more questions. I think it'll be a good time to talk.
Yes. Okay.
So one was, if there's no intervention at all, will R0 vary as days progress?
It should not. It will not vary, except if, there is probably no intervention, right, imposed by the government, but probably people will intervene themselves, right? If you start hearing about the disease and if you lock yourself down, so probably R0 will decrease, right? But there was some hidden intervention. But if life will continue by as usual, R0 will stay the same.
Yes. Yeah. Also, the recovery rate, people are saying the recovery rate varies a lot, for example, or the, mild infections versus severe infections. So population characteristics play a big role, right?
Of course, and that's why it's very important to model the age as well, right? So in Qatar, I guess we don't have a big fatality rate, and it could be due to the lowest age, right, or the young age of the patients, which means they will be mild infections or they will not be really critical. So integrating the age in these models is possible as well, and that will allow you to see these differences. And just going back to the question of R0, by the way, it could eventually start decreasing when all people gets infected, right? Because when the susceptible will finish, R0 will be 0, right? Because there is no one to infect anymore. Okay, so other models exist. I'm just going to the first one, right? This model could be scary for COVID-19, the SIS model. So you are susceptible, you get infected, and you go back to the susceptible. You don't get removed, which means you don't develop immunity, right? It happens, by the way, for the influenza. People will get sick several times per year. You don't develop immunity, right? So this, I hope it's not the case of COVID-19, even though we are seeing some cases, but I'm sure these will be rare, and I hope they will stay like this. The second model is the SEIR model. So you add a compartment that is exposed and that comes between the susceptible and the infected. And that is suitable when you have infectious diseases that has an incubation period during which individuals have been infected but not infectious yet. And that's the case of COVID-19. You could carry the virus, you have it in yourself, you don't have symptoms, and you will not infect people. I guess the duration will be around 4 or 5 days, something like this. You have it, but you don't infect people. So you move from susceptible to exposed. You have to model this because it's a kind of latent compartment. And if you are exposed, you don't infect people. So you move from susceptible to exposed, and from exposed to infected in a matter of time only, right? When you are exposed and you have the virus, you will get infected eventually. Or I mean, you will get the symptoms even if they are very mild, and then you move to removed. So this is one of the SEIR model, and this model could be even extended further to represent a more realistic scenario. This was published recently, so they added exposed, but they also added unreported. When you watch the numbers right now on all of these websites that shows the current numbers, there are many cases that are unreported, right? They are sick, but not much, so they stay home and they will recover by themselves. So these are unreported. And you put a compartment for the infected people, and you also add a compartment that could be very interesting. How many people need to be hospitalized? Because this will allow you to evaluate, do you have enough hospital beds to handle this? Do you need to create a new hospital, right? So it's important to put this compartment in here. Another model that was also recently published. So you add 3 compartments after the exposed. You split them by mild infection, and these likely will be removed very fast. The severe infection that will lead to the severe disease, and the critical infection that will lead to the critical disease and then removed. And just keep in mind, again, that this removed, it could be that they recovered, they don't have it anymore, or they diseased, they died, right, from this. Removed, they are out of the game. This model can get even more sophisticated, right? I will not explain a lot. I mean, this is a lot of compartment, but mainly, if you have a new vaccine, right? The vaccine could be good. It has some efficiency, right? If it's not good enough, what will happen? If it's good, what will happen? If you want to give the vaccine to 5% of the population or 50%, you know, the vaccines will not be of unlimited number at the beginning, right? Who to give the vaccine to and to slow the spread. And some studies, I guess, if you run some simulation, it will show that vaccinating 5% or 10%, it will really slow the spread of the virus. Of course, if the vaccine has some efficacy, right? So I just have 2 more slides. So the model we extended in here, it's an SEIR model, and Stefano will talk about this in a second. So mainly you have susceptible, they move to exposed with beta, and then with alpha to infected. But the thing in here, what realistically happens, that a lot of infected people will not be tested, right? For some reasons, because you know of the limited number of kits, of the testing time, of the hospital capabilities of doing this. And some people will get tested. And these are likely the people who have severe symptoms or who got in contact with some COVID-19 patients or were traveling to some areas where the epidemic started already. And from the tested, you will have the confirmed cases. And again, you could see that I was looking in France at some points, you had 1,000 cases each day, and suddenly there was 23,000 cases at once. This in general, you have the sample sitting at the hospital, you didn't test them yet, you couldn't, and suddenly you have the results that come up. So there is a delay in the testing results. So we model this from tested to confirmed, and after the confirmed, you will go to removed, either recovered or diseased. I'm not sure if I have time, but mainly the concept of these equations. I will just go over two of the first equations. The susceptible, again, you remove the people who get infected from that compartment. The exposed, you add the people who got infected, and you extract the people who move from exposed to infected. And I'm sure it will be worked out for all of them, but in general, whenever you develop such a model and you want to make sure that this is correct, all these terms to the right side of the equal sign, all of them, right? If you sum them up, it should be equal to the total population, right? Assuming a closed population without vital dynamics. So that's how you check that this model is correct. At least that's one aspect of the equations. And the other point that now Stefano will talk about is how to estimate these R0, right? There was a question, how much is it in Qatar? I said probably it's 2.4 or something like this. So these are estimated, and these are very important. Whenever you have a different alpha or beta that doesn't represent your population, your model will not give good results. So these are a couple of references that I used for this presentation and for these models. Thank you for your attention, and I will pass the hand to Stefano.
So while we do that, Saad, there was one question that I think requires some clarification. So the question is, so all infected person move out to removed after 4 or 5 days, as you say,
Yes.
they don't infect anymore.
Yes.
Please clarify.
Oh, okay. So actually, you know, when you are declared infected, so what happens? Okay, so you get the virus. I guess there is a kind of timeline that we're looking at yesterday. You get infected, you get the virus inside your body, right? So it takes, let's say, 4 or 5 days in general. That's the incubation period. Even if you meet with people, you will not infect much, at least for the first 3 days, right? And then after 3 days, you start infecting people. You start for 3 or 4 days. And after this, you don't infect people anymore. Even if you meet people, you are not infectious anymore.
Great. Okay. Thank you.
Okay. Thank you. Stefano, to you.
Hello, everyone. Let me share the screen. Okay. Thank you, Mohamad, for the very clear explanations on the SIR model. So I will take it from there to focus on the second part of today's lecture, that is about how to fit models, and in particular how to fit the parameters of these models, of the SIR models, on the observed data. So I will start with a quick motivation on why we should be very careful when fitting these models and be accurate, because these models are usually providing some forecasts, and these forecasts are used for decision making, maybe used for decision making. So it's very important that these models, for example, they may predict the hospital capacity or occupancy, so the hospitalization, and therefore in order to manage the hospital capacity, or they may forecast, for example, the peak, in order to know when we can release some of the restrictions that have been imposed. Therefore, we want to learn these parameters. Some of these parameters may be biological, therefore they are not going to change through time or across different countries. And other parameters, for example, the ones related to the restrictions, so to the social distancing, and for example, when you have a lockdown, so the number of average contacts is going, will decrease. Therefore, those kind of parameters we can estimate for each country, and we can also do simulation. For example, what will happen if we are going to reduce the beta, the probability of transmission of the virus between subjects. And so we can see that these restrictions is actually a very important aspect of this simulation, because it really changed the reproduction number. It changed the parameters of the model, and we can observe also on the actual data that different kind of intervention of restrictions in different countries have led to different results. For example, in Italy, where the intervention is considered a strong intervention, a lockdown, the reproduction number went down to 0.83, that is lower than 1. Therefore, we can see this curve going down. While in the US, at least for our estimation, the current reproduction number is still slightly above 1. Therefore, you can see you have this curve that is slightly decreasing, but it's slightly decreasing because it will decrease anyway, because the number of susceptible people will go down, and also the number of infected people, they will be recovered, and therefore then after some time the probability that a susceptible subject and an infected subject meet is of course lower. Therefore this curve will decrease anyway, but we can see that the slope is higher in this case. So it is very important to consider these two periods of time, and this is what we are doing in the model that we have developed in QCRI, because you can see that if you don't consider that we have two different sets of parameters, you will not be able to account for this difference. You will not be able to have two different curves, so you will not be able to fit the observed data. So what happened, for example, in this model for comparison, that is a model that gained a lot of popularity recently, is that they are fitting an SIR model on the data without considering that there are different parameters depending on whether the restrictions has been already applied or not. And therefore, it is not able to fit the two curves that that describes the current epidemic. And this can be seen also on the US data set, for example. So if you are going to just fit a bell-shaped curve on the observed data, you will not be able to do this in cases like that. So it's very important to consider this. So now going back to how do we fit these parameters. So given that our model is powerful enough so to consider all these peculiarities of the COVID-19 epidemic, we want, of course, the main idea in parameters fitting is that we have a model, we have a simulation of the epidemic, we have an SIR model, and we want to compare the results of this SIR model with the observed data in order to get a measure of how good is this model or how bad is this model in the case when we are measuring the error. And the idea is that we go through several iterations. By every iteration, we change the parameters in order to get a result that is closer and closer to the actual data. So we compute the error and we want to minimize this measure. So of course we can do this doing like a guesstimate for the parameters at every iteration, but of course this would not be an efficient way of optimizing. We want an automatic process and an accurate process to minimize the error by optimizing the parameters. So now to go into the details, the peculiarities of the data sets for the COVID-19 epidemic, we take as example the Johns Hopkins data set, and more or less all the data set available online, they have more or less this structure. They have the confirmed cases that usually is a cumulative number, and they have the recovered cases. So now if we are going to, for example, map these variables into the SIR model, so the susceptible can be easily computed simply by subtracting the infected from the total population. The new confirmer can be computed simply by we have the today's cases, and we subtract the total cases of yesterday, and the recovery we have from the data sets. However, this mapping is not correct, as Mohamad already mentioned, because we are actually comparing things with different meanings. So despite the word is the same, there is some ambiguity about what does it mean to be infected and recovered. So in the data set that we find online, when we find the daily new infected, it's of course the new case is confirmed in the last 24 hours. Instead, when we look at the SIR model, the I compartment, so the infected compartment, is actually the compartment of infectious period, of infectious subjects that are in their infectious period. And this infectious period, as Mohamad said, can be around 4 days or 5 days. So it's quite different from considering only the 24 hours. So this should be usually higher because they are going to accumulate over a window of over a time window of 4 days. And the same thing can be said about the recovered, because in the SIR model, the recovering period, it means the period that you are infectious. So when you are recovered, you are not infectious anymore. So of course, it's not something that from 1 second to the next second you are not infectious. There is some kind of distribution over time of the viral load. So you have a maximum peak, and then the viral load is going down, and you are less infectious. But the probability of infecting other people after 3.5 or 4 days is very low. So instead, if we consider what it means to be recovered in the data sets that we find online, so that means being recovered from the disease, from the COVID-19 disease, not from the virus. So it means they will screen you they will test you for the symptoms. And for example, if they check your fever for a couple of times, then you are confirmed as recovered because you are not showing the symptoms of the disease anymore. So these are very different also in time, because to recover from the disease, it may take up to 6 weeks if the disease is a severe case. So we must be very careful when we are mapping these variables. And we are doing this mapping because we want to measure the error in order to fit the parameters. So if we
Stefano, sorry to interfere, but so you're saying that what we observe in the actual data we collect, like from Johns Hopkins, other places, and the daily reports from the ministries, there's not a one-to-one correspondence within the compartments of the SIR. In particular, the I and R are quite different. S, of course, is you can perhaps estimate that. But I and R, they have different meanings in some sense, right?
Yes, exactly. So the word that is used is the same. Therefore, I think it can be quite confusing for someone that is approaching to the problem, to this task of fitting, or even just looking at this data, someone can get confused. So the meaning, yes, is different. And so yeah, for example, if we want to actually know the total infected from an SIR model, we could simply consider the people, the subject that are going out of the susceptible. So they just became infected, and therefore they are the newly infected cases. So and the cumulative number of infected can be easily obtained just by subtracting the susceptible from the population as a straightforward way. So then this variable, this value can be compared with the actual data that we find online. So another very important aspect that we want to point out is about the reporting lag. We are getting all this data. This is, something that is peculiar to COVID-19 because we are getting all this data like in real time. But we should consider that there is a lag between the time the time the subject is infected and the time that case is reported. And if we consider like the beginning of the epidemic, there is even a larger lag, delay between. The first cases have been tracked back to the 17th of November, but of course at that time they didn't know about this new virus. They were just showing symptoms of pneumonia, and then only on the 21st of January, then they knew about the virus and they reported the new cases. So if you look at the observed data, for example, for Wuhan, it will start from the 21st of January, but the first cases were long before that. But even if we take more recent data, there will always be a delay between the infection and the reporting. And this can be seen also when you look at the peak that is given by the restrictions. So when it starts to go down, it will start to decrease after, for example, 10 days or 2 weeks after the restrictions. So that delay is also given by the fact that there are like few periods of time between the infection and the reporting. So one is, of course, the incubation. So during the incubation, you don't have the symptoms. So you don't have the symptoms yet. Therefore, you will probably not be tested. So then you get the symptoms, and at that point you are like in the middle of your infectious period. So then, for example, the subject can call a number or get tested in some way. The sample is taken, is collected in a laboratory, then there is the testing, and then, there is some delay, and that this data is collected and finally is officially reported to the official channel, for example, of each country, of each minister. So there is this delay can vary, of course, depending on the country. It's not the same for all the countries, and sometimes can be quite extreme because sometimes data is collected through, for example, 2 weeks and then released all together. Like in the case of China, we can see some peaks sometimes, or even in the deaths, because they analyze the data posteriori and then they release this data. So it is important to consider this kind of delay in the model, in an SIR model. And therefore, so if we look at these bars, these are the actual observed data. But so we can see that the first time step is 22 of January. This is for the Hubei province. So the first time step of the data shouldn't be the same as the first time step of the SIR model of our ordinary differential equation system, because it should start actually from, for example, 2 weeks before. It should consider this period of time. And this is what we are doing, for example, in our model. So you start with the number of infection and you start with considering this delay, you start some days before the observed data.
This is a very interesting observation that because we're getting daily data, right? So actually there's some downside to that. Imagine you had a reporting every week or every 2 weeks, then many of these issues would, things would smooth out a little bit. But because we're getting data every day, things become quite, we have to be very careful when we're applying these, these models, right?
Right. We are getting data every day, and we are also trying to make short-term predictions. So it really matters if we are starting 2 weeks, 1 week before, or yes, after. So because if we are going, for example, to predict the peak, of course it matters a lot. So one thing is in 10 years from now to analyze this data, having the whole data, and another thing is day by day to get this data and do this short-term forecast. Now the next important the key point here that is related to this epidemic regards the reporting ratio. Because as already mentioned by Mohamad, we can have a very low percentage of reported cases. So we must consider that this proportion, this ratio is not known. So this should be one of the parameters that we want to fit, should be part of the parameters. And this is because we know that there are a lot of asymptomatic cases. We know that there are a lot of very mild cases, a big percentage of the cases. Therefore, it is very probable that many cases go untested and unreported. So we should consider this. And it varies a lot, so it's difficult just to estimate one reporting ratio. It depends on the country. For example, 33% is in the case of Germany. They estimated that one case out of 3 COVID-19 cases was reported, but it can go as low as 0.1%. So if we consider this, it means that in the background, in our SIR model, we are actually simulating the real infection. So the total cases of infected subjects. In Italy, for example, we estimated that this percentage was 23%. And if we show what's behind the model, so how is the real curve of newly infected, daily new infected cases, we see that the curve is much higher than the one that is shown. However, what we want to compare is, of course, only the observable one. So what we are going to compare in order to fit the parameters is the compartment of the confirmed cases. So this is the same diagram that we have seen before. It's an extended model. It's our extended model of the SEIR model. And here you can see that we are not comparing all the compartments to compute the error, the loss, but we are comparing only the confirmed compartment. So only that ratio of infected people will be compared with the observed data, and the loss will be computed on that. So we have all these other compartments that are actually being simulated. So they are in the model. We could, for example, have a look at those. But when we are going to compare for the optimization, we only use the confirmed. So that's the observable one. So now to give an overall idea of...
Sorry, yeah. Stefano, there was a question here which could right time to answer. So the question is, how do you estimate percentage of reported cases?
So, okay, here the idea is that we have several parameters and we want to fit this data. So of course we can also set some bounds. So we can say, for example, these parameters is in this interval, and we also have some intervals for we can somehow doing a constraint on the parameters fitting. We know, for example, the biological parameters that are more or less the same. So in that way, we know the system, the optimization process will optimize only for this value, but of course by optimizing for this variable is going to optimize each parameter. So I will show what's the actual loss if we move around the parameter space when we change parameters. And you can see that for many values, we can have a low error. So for example, you could have a lower ratio of tested people and a higher value of RT, of the reproduction number. And this will lead to a low loss. But in the end, when we are going to optimize for the minimum loss, we can actually find the best parameters, and this includes also the testing ratio. So the overall optimization looks like this. So we have the ODE model, the ordinary differential equation model, that is defined by derivatives. Then we take this model. We need to solve the model. We need to get the actual function for each time step. So we can apply like a numerical approximation method to discretize each time step and get the value for each time step. And then once we have these values, we can compare with observed data and we will obtain the loss. This loss is then used to change the parameters in an iterative way. So now how this parameters optimization works, I will show now, like the next couple of slides may seem a little bit more technical or complicated, but I think there is a key message here that we want to convey. So bear with me, and then we will go back to high-level content. So here we are showing, if you look at the top left plot, this is the actual loss, the actual error that we get from the fitting for all the possible combination of parameters. Like let's say we are setting a testing ratio of 0.2, so 20%, and we have an RT, so a reproduction number of 0.6. So we can look at this surface and know how much is the loss, how far away from the observed data is our model. So the idea is that we have this loss surface in this case, and we are in any point, like we start from some point of the parameters value, and we want to go down this surface in order to search, in order to find the minimum loss, so in order to fit the data in the best way. So in order to do this, like in order to plot this this surface, I had to try all the combinations. So it was like a brute force method that, of course, we want to avoid, and it won't be feasible at all if we have, for example, many parameters. And this happens if you have a complex SCIR model, like an extended model. You're going to have many parameters, and you cannot do this. So here, what I'm introducing here is a very well-known technique, the gradient descent, that is at the base of all the modern optimization techniques, including machine learning and deep learning. So instead of computing the loss, the error for all the possible parameters, we can compute the gradient, that is the slope of this loss in each point. So let's say we start at some point. So this is the plot for the gradients. We start at some, we initialize at some random point. We compute the gradient, that is the slope of the loss. So how it's going to increase if we move increasing p-test and RT. And of course, here we want instead to move in the opposite direction. So we don't want the error to increase. We want to minimize the error. Therefore, we can follow these arrows in the opposite way. And in this way, we only need to compute the gradient at the exact point where we move stepwise until we find a value of loss that we are comfortable with. And then that will find us the parameters value for the parameters that we are trying to fit. So this is, of course, a much more efficient way of doing optimization. So this means that we need to compute the gradient of a function that can be very, sometimes it's not feasible if the parameters are a lot of parameters. Like if you ever seen neural networks, in each node we can have hundreds of thousands of parameters, and this will not be feasible. And the same is for our ODE solver. So for our system, even if we have less parameters, we have like iteration over time, that this can be very tedious. And I mean, we cannot do manually. The best way to do this, the most efficient way, that is the modern way of computing the gradient of a function, is through automatic differentiation. So I will not go into details of this, just to let you know that there are packages out there for many programming languages. So you basically, you can define your own function. If the function is differentiable, this function, these packages will automatically compute the gradient for you. And this applies also for very complex functions. If you are going to consider many parameters, this will still be able to compute the gradient and therefore to do an effective optimization with very complex functions. So now going back to the results and now to conclude this part of the lecture, here I want to show some validation for the model, because of course it's nice to have a model that fits the observed data, but the value here is to actually forecast unseen data. So how does the model do with the unseen data? So here we can, for example, train our model until the 7th of April. And so we have only this data that you see, the green line, and then we can forecast with our model for how long we want. In this case, it's 100 days, but could be even years. So then we can wait, or of course we can just split into training and testing set, and then we can see how the model it actually did on the real data. So we can see that in this case, it did pretty well, even if just by looking, someone would say that we could have a steep decrease. Instead, the slope is much more like our model predicted. And you can see it from the red line, that is the actual observed data. It's fluctuating around the blue line, that is the model simulation. So the same we can apply for other data sets. Here we have South Korea, because of course we need a data set with enough data for the training, for the testing. And here is the same thing. We could say that the fitting doesn't look very good, but here the error that we are computing is not only point-wise. So we are not trying just to have an accurate model point-wise for each time step, but we also want to optimize for the total number, for the cumulative number of cases, in order to take into account that sometimes the delay in reporting can be less, sometimes can be more. So cases can be accumulated and then can be released all together. So that's why the fitting here is an optimized fitting. And if we look at the results, I think this is also very good, because the observed data is, sometimes is below, sometimes is above, but in the end is fluctuating around line, and in the last month is quite overlapping with our prediction. So if you want to see what is the prediction, for example, for other countries, and also if you want to have more details about how this system works, we have provided a website with a one-page paper for more technical details, and that you find the link here below here. Thank you, and I will give back to
Stefano. The general observation is that all these models, it goes up very quickly, but comes down very slowly, right? That's seems to be the pattern, right?
Right, because in this case, it's, the decreasing slope is given by the restrictions more than by. So if we had, for example, a peak given by the fact that there is a large outbreak without any intervention, and therefore at some point the number of susceptible people and the number of infectious people will go down, because a lot of people will be immune. They already had the infection and they are not infecting anymore. Therefore, the curve will go down more quickly. So, of course, depending on the R naught. So here the R naught, of course, is high, but then so it's much higher than 1. It's around I think 4. But then the restriction, when you apply the restriction, is maybe it's still closer to 1. That's why you have a slope that it's not so steep.
Okay, thank you. So yeah, I have a few slides that I would like to share, and so can everybody see? Can you see my slides?
Yes, we can, doctor.
Okay, great. So yeah, so thank you, Saad and Stefano, about the model. I just want to say a few words about spatial modeling. You know, in all these models that you've seen, the modeling has been carried out at what you can call at the aggregate level. So, for example, at the country level, and you know, or even at one state level. But often when we are doing this modeling, we're making assumptions. And when we do this modeling at the aggregate level, then we are making some kind of a uniformity assumption. Okay. But as we know from our just watching the news that so the R naught is not the same across regions, across age groups. And so that's why, you know, many of these models have had, people have asked questions about them, how accurate they are. And I think, you know, the general perception in the community is, the research community is that uniformity leads to systematic errors, you know, and you might assume that because of uniformity, they'll average out, but actually doesn't average out. Okay? And especially, you know, spatial geographic factors can make a substantial difference. Of course, age factors can also make a big difference, but I want to sort of focus briefly on the spatial and geographic factors. So here is one example that you know, from Sydney, and the top row shows basically the profile of testing in Sydney, and the darker color, the more testing there is. And the second row, the bottom, it shows the actual cases. As you can see, one thing that's obvious is that the spread is not uniform; it's very heterogeneous, right? And I think that's very important to realize that you know, heterogeneity is a key component. It's not something that can be overlooked. And I think the way the testing was done. So, for example, if you look at March 25th, the you know, the testing graph, and then the new cases, which is below it, and then you move from March 25th to March 12th, you can see that you know, you suddenly start seeing lots of green. That means the number of cases is growing a lot. And then what they did in Sydney, they did very extensive testing, but they did testing in a more not in a uniform manner. You know, they focused their testing based on the hotspots in the region. And then when they moved from April 12th to May 5th, the testing increased substantially, but the number of cases did not increase that much. So they were able to use very strategic testing. So here, there's only one case where this light green becomes dark green, and the rest of the graph looks similar. So they were able to control uh, uh, the epidemic to a certain extent by having you know, spatial testing. So now let's move to see how one would model this. You know, so for example, suppose we are in Qatar, right? And that's what we want to model, right? So we have, you know, the Hamad Airport, West Bay Industrial Area, we have Al Khor, we have Dukhan, and we want to actually treat them as separate entities. You know, often you can say the first cases, let's assume, land at Hamad Airport, and then they propagate to different parts of the country. So one thing you realize is that each region, you know, will have its own dynamics. So essentially, the equation that Saad showed, I mean, you don't have to know the details of the equation, but each of them will have their own equation. Each one of them will have their own sort of beta parameter. The gamma parameter will not change. The duration of the infectiousness will probably not change, but as we know, all these regions have different populations, different density, so they need to be captured separately. The other thing, of course, is this coupling between the regions. So there is coupling between industrial area and West Bay, industrial area and airport, Al Khor, Dukhan. How do we actually capture this coupling between the different models, right? And of course, as you can see, once you move to the spatial world, the complexity really goes up, because now you have as many sets of equations as the number of regions you're trying to model. The other thing is, what is the right spatial granularity? Do we model it at, at this level, at the area level? Do we go much deeper? Or do we even actually go at the individual level? We treat each individual person and model them. What is the probability of them being infected? So I think, this often leads to what's called the Simpson's paradox, because depending on the level of granularity, you can actually you can arrive at different conclusions. So one has to be very careful about modeling spatial data, but I think it's important that it be done. So how can we actually, in the case of Qatar, is there a way we can get a handle on the spatial dynamics of mobility? So it turns out that as part of the strategic planning, the Ministry of Transportation and Communications, they actually produce what's called the origin destination matrix. The origin destination matrix basically captures the traffic profile between locations in Qatar. So how, in a typical day, how many people will move from West Bay to Education City? How many people will move from Al Khor to Dukhan? All these, they have very sophisticated ways and it's a very carefully done data collection, estimation, sampling to produce this, what's called the origin destination matrix. In the case of Qatar, what they've done is they've divided Qatar into 1,839 zones. And so thus this origin destination matrix is a matrix of size 1839 by 1839. And just to give you a sense of how big these areas are, these traffic zones are, they are, for example, the whole industrial area consists of 30 zones. Okay? And we think that this origin destination matrix just on its own can be used for as a policy tool to control the epidemic. For example, it can be used for incremental planning for unwinding of the lockdown. How do you unwind the lockdown? How do you make sure that regions which are historically been very highly connected based on the origin destination matrix, you keep the restrictions there. Okay, it can also be integrated into the modeling, as I just mentioned. And of course, you can use it for selecting areas for testing, as it was done in Sydney, or it can, even in other parts of the world. So here is the origin destination matrix of Qatar. And so this is the rows are origins. That means, where people leave for work or for entertainment or, just for travel. And the rows are the columns are the destinations. And each dot represents that there is travel between the origin and the destination. And as expected, you'll see a very strong horizontal line for Hamad Airport, strong horizontal line, even for Al Khor, an industrial area. There's also spatial locality. You can see that there is a cluster of city points where people mostly travel close to each other. So I think this information can be exploited. So how can this be done? One thing is like what Saad showed. You can actually take your origin destination. Again, you don't have to understand the math here. Essentially, what you do is you incorporate the origin destination matrix into your equations, and then you can simulate. You can run these equations in a simulator, and then you can see how the SIR curve or the infectious curves will change. So for example, here we've shown on the right-hand side how, as you control the alpha parameter, that means essentially what you're doing is you're enforcing a lockdown at different intensity. So if you, for example, make alpha equals to 0, essentially what you're saying is that there's complete lockdown. And when alpha is equal to 1, you're saying there is no lockdown. So as you can vary alpha, you can actually start seeing the impact of, it can be a policy sort of driver to see how by changing the interconnections, slowing down the traffic connections in the city, you can actually force the curve to flatten. So again, it can be, as I said, used rather than having blanket lockdowns, you can do very precision lockdowns. So here's an example of what we did was we sort of we did a simulation by injecting some infected cases at the Hamad airport, and then seeing how the number of infections will spread. Again, it's very clear that it's not uniform. You know, it's disaggregate. You know, it's quite heterogeneous, and I think this information should be exploited, and it should be made part of your standard modeling toolkit. Similarly, you can, even without doing any simulations, you can actually look at the areas of high connectivity. So we looked at, the top 10 areas in Qatar by connectivity. And of course, Hamad Airport comes up, but, the other areas like Al Khor shows up. And of course, the areas of industrial area, parts of industrial areas which show up. And also this small area here in the middle, which seems to be highly connected with the rest of the traffic, with the rest of the regions in the country, shows up as highly connected. So this actually, in computer science, there is this notion of centrality, or, the way the Google works, the way they rank their pages. This is a very similar idea. You can actually rank your zones based on connectivity and also what's called centrality. And I think this information should be used to extend these to extend standard epidemiological models, tongue twister, to capture the real essence of what's really going on. So just to conclude, I think spatial modeling needs to be incorporated into the next generation of modeling. But what happens is that it leads to increase in model complexity, because every region has its own dynamics, and the dynamics are coupled. So that needs to be captured in. And of course, because you have many more equations, you also have many more parameters, and that increases the computational complexity of solving these models. But we can use, as Stefano mentioned, we can start using these modern automatic differentiation techniques and tools, which have been widely used in the machine learning and the artificial intelligence community, to come to our aid. So I think there needs to be a bridge between the standard modeling techniques that are being used for all the standard compartmental models and modern machine learning techniques. I think they can benefit a lot by talking to each other and working with each other. So that sort of concludes my short part, and I'm happy to take questions for us or for any of the three. Okay. So there's one question which I can mention. Is there any real world implementation of spatial model, or just we have simulation results? I think at the moment we just have simulation results, at least the one we are aware of, but I'm sure there are other groups out there who are looking at spatial models. Okay, so there's another question, how Sydney approach was better than SEIR model. Yes, I think what I showed was not necessarily the SEIR model for Sydney. It was more about how they had used spatial information to do testing, but I'm sure they're using SEIR models too. Thank you. So yeah, okay, great. And so any other questions? Otherwise, I think we'll wrap up for the. Okay, so there's one question. If you could map the known cases by residential address, it would be helpful. Yes, I think if we had the geographic locations of the cases, but I think it's then yes, that could be potentially very useful. But it depends upon the policies in different countries, how much information can be released. So in some areas, in some cases, it is being released, but in some cases, it's not being released. Okay, great. Again, thank you very much, Stefano and Saad, and hopefully we'll see you again on Monday for another edition, and which will be on the use of AI and machine learning for drug repurposing. Okay, thank you very much.